right. I think we're doing good. And we are live. Beautiful. Okay. Sweet. All right. Let's get this party started. We'll wait a few minutes just for people to show up. But it's a wonderful weekend here. All right. So we'll give some time for some of the live people to show up. But let's see what we got here. So last time we were just working on little bits here with building out a deck of cards and coming up with a way to shuffle them. And we left off with a really, really horrible, unpure randomizer that we're using. So today we're going to focus on building our own random number generator that we can own the seed with, so we have complete control over that. And we will take it, so we'll probably spend a lot of time talking about the LGC or LCG. We're going to be using a linear congruential generator and figure out how we're going to use the state monad to actually keep track of that seed. So every time we pull a number from our generator, we're actually going to use our seed to pull that back, right? Oh, good. We finally got someone watching. Yay. You know, this has been very humbling for me. I'm used to having 20 to 30 people at a time, and last time I think we maxed out at 4, but I don't know. I'll start building my fan base here as opposed to on the other live code site. But so I guess we can get started with the LGC or LCG. So we're going to build our own random number generator, and we're going to use this. It's called a linear congruential generator, and we'll just build this step by step. So it sounds all silly, like that name. It's a little ridiculous. May or may not make a lot of sense depending on how much you remember of like junior high math or whatever. But everything we need to know about this generator is in its name. It seems like it's complicated or whatever if you're not familiar with mathematics talks, but really it's so simple. So it's based on this formula, and it's a sequence of numbers, or I'm sorry, this equation. It's a sequence of numbers that every time you get a new number, it allows it to, or it seems like it's random every time that you call it, right? So I guess we can break this apart line by line, or bit by bit. So there's two parts to this, the linear and the congruential. This part is the linear, and I don't know if this looks familiar, but if you were to replace this with a y, and replace this with an m, and then keep it x, and then replace this with a b, you might recognize this as the slope-intercept form, or y-intercept form of a linear equation, right? So this would be where c is here, this increment, that's actually going to be your y-intercept, and then a in this is the slope of that line, right? And this would be y. So basically what this is saying, this is self-referential, right? So it builds a number sequence. So simple. And the congruential part comes into this, but we'll look at this part right now. So if you can think about this, we basically draw a line, okay, based on this equation. So we have a slope to that line, and then we have some x or some point on that line in the x-axis, right? And then where that c is where it crosses the y-intercept, or where it intercepts the y at 0, okay? So what we do is we will take, notice how it's n plus 1 and then the n here on the x's. We're basically going to calculate what the y is, and that's going to be our next number in the string. And then when we want the next number, we take that y and plug it into the x here, and then we get a new y. So we basically take the y from the other part and plug it back in and get a new number. Make sense? So the part that I think is beautiful about this is everything that's generated will always be generated on that line. It's very neat, very cool. And then from there, since we work with computers, like this line would stretch on to infinity. Well, we don't have an infinite amount of space that we can just keep grabbing lines. Like when we run into the size of what our maximum integer could be, then we start getting all kinds of crazy results with negative, it jumps into the negative values, or maybe every now and then we might overflow and it starts thinking it's a floating point number and it's no longer an integer because we're going out of the bounds. Well, that's where the congruential comes into play. Now, if you remember from, how would you say, geometry, when you had two angles that were congruent, there might be, two rays or two angles, but if I can rotate them to where one of their rays matches up, and if the other ray matches up, we say that those angles are congruent, right? They're the same thing. Well, we get that with a modulus operator too. So if you think about, like, let's just jump into Node real quick. Okay, so here we are in Node. If I were to take, 3 mod 7, oops, that's 3 and 7. If I were to take 3 mod 7 here, where is that? It's this feller here. I'd get the 3. But if I were to take 10 mod 7, notice that's also 3. So we did the same sort of thing, right? We took the angle, like the same thing as if we were to find if two angles are congruent. All we did was transform it or move it along the line and line them up, and we see that they're the same thing. So in this world, 3 is the same thing as 10 whenever you have the mod 7, if that makes sense. So what this is going to create when we get into this is it's going to get to a certain point of whatever our modulus is, and it's going to drop back down and create that same line at the 0, if that makes sense. So we end up with this sawtooth wave, and then every time that we call x, it's going to give us back the point y on that line. And then that's going to be our next seed. So this can keep stretching on to infinity. Well, this can keep stretching on and on and on, and we don't have to worry about overflowing our type because we're going to ratchet it down, right? So now there's a lot of problems with this, or there's a few problems with using something like this. And it has to do with the periods in which these things oscillate at. Eventually we might run into the same sequence and things like that. So let's just implement this real quick just so we can kind of see what it looks like, right? We'll go ahead and take log here. And we will look at the actual formula here. So we want some x. So we'll do const and we'll say rando just for now. And we'll say that rando is a number. Let's see here. Or we'll say rando is a function that takes some seed. We'll just call it a seed at this point. And then that's going to get us back our x plus 1. And we need some sort of multiplier here. So what we're going to do is take this and we'll have something called mult. And this will be our multiplier. And we want to multiply that by whatever our seed is, right? So when we get our seed in, we're going to multiply that by the seed itself, okay? Now, we need to have our y-intercept. So in this linear equation, we need to provide what our y-intercept is here. And here they call it the increment. So we'll call that, we'll just call it increment here, right? And because of order of operations, we don't need to worry about this. It'll do the multiplication before it does the increment because math is awesome, right? So now we'll just create and we're just going to use var here. Actually, let's use let because we're going to get rid of this. This is just to kind of show you, what we're doing. So we'll come up with a multiplier times 2, and here let's create our increment, and we will make our increment be equal to 1. All right, so basically it's going to cross the y-intercept at 1, and from there we're going to have a slope of 2 on it. So rise over run and all that stuff that you remember from high school or junior high school or whatever. And then we also need to create our modulo, or our limiting factor, right? So we're going to make this a 10. And how we'll do that is we'll just mod whatever our mod is. Oh, why do you keep doing that? That is so ridiculous. All right. So now we have everything we need to start generating random numbers. But we might run into a problem with this, right? So but just to show you kind of what it does, we'll do rando, and we'll bring our seed in as 45. We'll make our first seed 45. So that gets us back a 1, right? So then if we feed a 1 into that, that would get us back a 3. And if we feed that 3 back into it, that'll get us back a 7. So then if we feed that 7 back into it, that'll get us back a 5. And it'll keep doing that. So that's how we get these pseudo-random numbers. And we could start with anything. So we could do like date.now and go ahead and pull a large number based on that. And as you see, we get different values for every one of that, every time we get a new date now. Okay, so this isn't very fun. It's neat, but I have to manually do this. So let's go ahead and make this rando. We're going to go ahead and make it a generator function, right? So then we have something that we can actually iterate over and do all that. So we'll bring in our initial seed. And from there, let's go ahead and make this a generator function. We are going to do let x equal seed. And so that way we can get this into a variable or anything. Or so we can get it into some persistent state that will keep using that. And then we'll just do a while. We want this to be forever and just run forever and ever based on that. So here we'll end up with our while true, and then we will yield out, it's called spelling, we'll yield out x is equal to, and pretty much just take our formula here, all right? We don't need any of, we don't need any of that. So we'll just take that out, and we'll go to the end here, paste that in, and then we can get rid of all this junky junk here. So x is assigned but never used, so that is going to be not our seed but our x. Okay, sorry about that. All right, hopefully that makes sense. So we get this going, and let's go ahead and we'll seed this bad boy with 45, right? So now, and actually, let's do this. We'll create a generator called gen, and we'll just go ahead and seed this. Again, this is kind of imperative. It's kind of weird, but we're definitely going to move this into a more functional. It's just easier to explain this in these imperative terms, so or to play with it, I guess. But don't worry, we'll go ahead and make it all functional here soon. So or declarative, I should say. So we'll create a generator, which is just rando, and we'll put this at 976 to have our little generator. Okay, so now this gets us back our generator. And what we want to do with that is, now that we have this generator is basically going to be an iterator that every time we call next on it, it's going to give us back what we need, right? So we can just do gen.next, okay, and it'll pull that. So that gives us our 3. And every time we pull that, it's going to give us our 3, right? So then we can do this a couple times. Let's just do this. Okay. And the thing that's neat about this, though, 3p, you see that we always get the same values back. It's always going to be 3751, 3751, 3751, right? So we'll get that back every single time. But now watch what happens. Then we'll start looking at some of the problems of these, right? Oops. So we want to y and then y and 10p that. So one of the things you'll notice, and this is what's called the period of these, this is one of the reasons why people say don't use math.random or don't use things like that to actually create, how would you say, things for cryptography or bits along those lines. You don't really want to use generators like this because you can run into these states of periods, or you run into these periods. Like every LCG has a period. So if we have 3, notice we pull a value from it. It has a 3, a 7, a 5, a 1. But then that 1 gets us back a 3, which then starts it all over again. So it starts oscillating on that same sequence. Now, when we go to implement this ourselves, we're going to use much larger numbers, a more steep slope, and a much higher limiting factor. But no matter how high we push that, there's always the chance that we're going to run into our period very quickly. So, and that's why if you're pulling a lot of random values from these types of generators, like maybe you're generating IDs or doing things like that, you're going to run into a point where you start generating the same sequence of IDs over and over again. And with just a little bit of, how would you say, analysis, signal analysis on the waveform that's generated from this, it's very easy for a bad guy or someone that's just curious to be able to predict what your next number is going to be. So that's why typically things like this aren't used. So this is also pretty ugly here, having to call gen next. So let's make a quick take function here, right? So we'll just make this take function that takes an x and some generator. That x is pretty much going to be our seed, our initial, not seed value, I'm sorry, that should be n. But that's going to be our, the number of things that we are generating. And then g is going to be the generator that we're going to use. So to do this, all we really need to do is get an array and fill it. So if we want to take like 10 values or whatever, then we can just create a new array and we'll put in what our n is. So this will get us an array of 10. It'll basically just give us an array with 10 nothings in it. And then from there, once we have kind of that array filled out, we'll go ahead and just fill it with null, right? So now what this is going to get us is an array of 10 nulls. Then what we want to do is we'll map over this, and we don't really care about the nulls, and because this generator is going to give us the values and things like that, all we'll do is, how you say, do g.next, and then we'll pull the value out of that. Notice how over here on the right, the generator will get you back a value and then whether you're done or not. So this will basically just pull the value out and then add it to that, right? So now we have this, and we'll get an array back, each with random numbers, and we'll only get the 10 that we want. And it'll keep it from spiraling out of control. So now all we need to do is we'll take our generator, and we will take 10 of these and pass in gen. And then you notice we get back the same values. So another thing we can do, let's go ahead and just put this to 45. And you see that different values will get you different periods. In this case, it's pretty much the same. Let's see if we just put 5 in. Yeah, see, eventually 5 will get you to 1 to get you to there. So this isn't really cool. So let's go ahead and change our modulus here. And we can increase the slope of this as well. Right? So now it takes a lot longer to get that period. And it's getting us numbers between 0 and 100. 0 and 99, right? What's this while about here? Oh, extra space, sorry. There we go. There we go, that's looking pretty now. Okay, so let's go ahead and take 100 of these and then see when we start running into stuff. So see, this still has a period, even though we've increased it, but the period's shorter. Eventually, we're going to get right back to 5. So it'll go 5, 16, 69, all the way up until we get to 48. And then 48 is going to lead us back to 5. So even with numbers like this, it's still going to be a little trying. Now what we're going to do is use different values that are that have certain relationships to them, right? And these have been around, I think, since the 40s, maybe the 50s. So there's a lot of experimentation that's been done with these to get the types of values that work well in the limited size that we have with computers, like for a specific type, right? So this handy-dandy Wikipedia provides us with some really good parameters that are used in different libraries, right? So we're going to go with we are going to go with this the one that's used by GCC basically. There's reasons for that, and as we're building it out, I'll get into what those reasons are. But basically, we're going to use this as our multiplier. Our increment is going to be this, and this is going to be our modulus. Now, there's some really cool things when you have a base 2 modulus, because you can do some cool little tricks with, how would you say? You can do some cool little tricks with doing mods and stuff when you have that bit arrangement, right? So let's get rid of some of this stuff, and actually we'll go ahead and let's just plug these first two values in. So we're going to get our multiplier, which is here. And there's a special relationship between these numbers that has to do with how they factor with each other that will lead to less collisions, if you will, right? So we're going to add this in. We want to keep x the same, and then for our increment, we're going to use 1, 2, 3, 4, 5. Make it super simple, and that's going to be where we intercept our y, right? So we don't need this anymore, and we don't need this because we're not going to be doing these random values. Okay, so before we do this, and actually, let's just do math.power for this, and I'll show you why we're doing what we're doing here. We'll do math.power, and we'll take 2 to the 31st, and then we want to subtract 1 from that, right? And that'll get us this number here. So we're going to take 2 to the 31st and then subtract 1 from it. Soon we'll go into the reason of why we're setting it up like that, because it kind of plays into this algorithm. So now if I save this, whoa, we get much bigger numbers, much bigger numbers that we can use and play with, so to speak. So these are the numbers that we're going to be using, but these aren't the random numbers that we're generating. This is actually the seed that we're going to provide. So once we get everything calculated, we're going to base a number off of this seed, and we're going to return this as the next seed to be run in the next iteration, or the next time that we call for another number, right? So let us, we'll set this up, what's the best way? So we need to provide two things. We need to keep track of this seed, and on top of that, we need to base some sort of calculation on this. But before we get into that, let's, sorry, I'm getting ahead of myself. Before we get into that, one of the things we want to do is change around this modulus operator, right? So like here, it's not going to matter so much because we're limiting and we're not going to run into a negative number. But once we start manipulating all this, there's a really good chance that we could very easily overflow and get into two complements mode, where we're like all of a sudden have negative numbers being plugged into our equation. And we don't really want those. I mean, they're fine, it works all right, but we don't really want those negative numbers in there. So one of the things we can do is force, one of the neat things you can do is force, how would you say, the JavaScript number, the number that we use, to always be a 32-bit signed integer. And you can do that just by doing bitwise math on it. Now, whenever you have anything that's to the 2 to the power of n, instead of getting the modulus on this, you can just use an and get back the same value, sort of, -1. Or it'll give you a value from 0 to the what you're expecting -1. And we'll look at that real quick. So let's go ahead and make a quick function here. Just so we can kind of look at some values here, we're going to call this 2hex. And 2hex is basically going to be a function that takes some x, and that's going to be a value that we're going to represent in a hexadecimal fashion. And forgive this isn't really something I would put in production code, but it's something that works well, right, for demonstration purposes. So we'll do an x to string, and we'll to sting. And then from there we'll provide a radix for this of 16. It's rad. And then we're going to check the length of that, right? Because we want to be able to represent these as the bytes that they are. So what we'll do is get the length of this, and then we'll check it mod 2 to make sure that it is not to see if it has 2 values or not, right? If it doesn't have 2 values, because we always wanted multiples of 2 to represent a byte with hexadecimal, then we'll just go ahead and append a 0 to it, right? Or prepend a 0 to it. So we're just going to check the length here, and then we'll do that mod 2. And then from there, if it is mod 2 and everything's good, if it comes back as 1, then we'll go ahead and add a 0. Otherwise, we'll do nothing. Okay? And then we still need to get this value back into it, and this is why I wouldn't use it for production bits, we're going to go ahead, sorry, my little kitten jumped up on there. Otherwise, we will return nothing. And then from there, we want to go ahead and just do another one of these, and then an x dot toString. And again, we'll do the 16, so it'll put that into hex. Now, this isn't the best of ways to handle this, but again, for demonstration purposes, it's totally fine, totally fine. So let's go ahead and see what this looks like. Say I were to take our mod. So let's do 2hex, and then we'll take our mod. So you'll notice down here, we end up with 7f. And that gets us our actual hexadecimal representation of the number that we're using for our modulus. Now, one of the things that you might notice, if we were to put this in binary, we are, like I said, it brings it to a signed bit, right? So the reason why we have to, or a signed integer, a signed 32-bit integer. So we always need to make sure that that first bit is always 0. Otherwise, it puts us into negative land, or gets us into negative mode. And we don't want any of that for now for this algorithm. So that's why we do the -1. If we didn't do the -1, it would get you back, it would be 8f. So if we look here, let's get our calculator. So if we do 8 clear, I want this in 16. So if we do 8f, and it's one more f. Oh, hold on. That doesn't seem right. Oh, it's 0, sorry. What are you doing, Ian? Of course it's not right. So what we want is 0, 0, 0, 0, not that. I'm so sorry. So we want to go 8, 0, and then a couple zeros, right? Now notice what this did is it set in a 32-bit fashion, it would have set this to a negative. So this would have been the 2's complement of that. So to see what this would be, it would basically be a negative number, which would be the inverse. It should be the highest negative number. So we don't want that. So what we want is that -1 in there. And that's why we have it in there, is because we have to deal with only having a 32-bit value. So cool, that's our mod, that's that. So now what we can do to force this into 32-bit, and because we're doing something that is that math to the power of 2, we can then and in that number that we have here. Oh, come on. And we can just plug that right in here. Sweet. So now this should get us the same bits that we were getting before. Now we don't need to have this mod. And we have 741 at the top there, and we have 109 down at the bottom, right? Oh, it didn't give us the same value. Why did that not get us? Oh, because I should have did it the other way. It should have been, it would be the same number. What is going on here? Wow. This keyboard's been acting kind of screwy. All right, anyway, yeah, it would have been the same number had we have made that the actual 8888 bits there, and then modded it in, but we're not doing that. We're now doing the pointwise, so it's going to shift everything from 0 to the top, or because we're doing the bitwise stuff there. So like I said, we needed to run 2 operations, and this is going to become important later, but there's 2 things we want to do with this. So we want to set what our next seed value is going to be, but then on top of that, we need to calculate out some sort of value from this, right? So we can do this by using the, how would you say, horrible comma operator. So I don't know if you're familiar with what the comma operator it does, but it's basically, or a comma expression, it'll basically run 2 things or multiple things, and it'll keep doing it like, and then return whatever the last thing is for the result of the expression. So since we have to do 2 things here, all I need to do is use the first one to set x, so that way x will be set, and then we want to give back a number, right? So the number we can give back, so the number that we give back is going to be, and again, we really want this to be a value from 0 to 1. So right now you see how everything we're giving back is the seeds or the integers, right? So since we have, we're limiting to this and no number will ever be bigger than this, we can normalize this by dividing whatever this is by what the limit of our bits are. And that's going to get us a value from 0 to 1, which is what we want. And we want to float in that. So the easiest way to do that is with division. So all we need to do is divide this by this number. And this will get us back what we need, right? So now you notice we have, it goes 2.6, blah, blah, blah. Now we have random values that work with this. It's not going to give us anything greater than a 1, and it won't get us anything, how would you say, like a negative value after that. And all that's doing is it just limits it, right? But we run into a problem, and we don't really see it with here. And with this float, but if we were to actually look at the way that the bytes were laying out, you'll notice as soon as we get that first bit set to 0 on the, what would you say, the most significant bit, you'll notice that it always stays 0. And it'll always give you an even number whenever you go to, how would you say, calculate this or whatever. So just to show you what I mean, and actually we can see it with more whenever we actually go to limit this. So let's create a quick little limit to function, because we're going to want to limit to a certain size for our array and stuff when we actually start, selecting random things from a deck. So we're going to set up our limit here. We'll call this limit2. And this is just going to be a function. It's going to be a curried function that takes the limit. It's basically what we want. And because it's going to be a curried pointwise function, or point-free function, we need to go ahead and set this up for passing the data in last. So this is the number that we want to limit to. So all we need to do now is just math.floor, and we'll math.floor x times the limit. And this will get us a value from 0 to that limit minus 1. Okay. So now all we need to do is we'll use this same take function. We'll go ahead and take 20 of them, I guess. And let's go ahead and expand this. I'm hoping all this makes sense. I'm trying to, this part, I just think it's good to know what we're doing. So I'm trying to go through it pretty quickly. But if anything, if you're like, wait a minute, what the heck's going on? Please stop me if you have any questions. So you can just hit me up in the chat. So we'll do take, and now that we have our list of values, let's go ahead and map over them, and then we will limit those to limit2, and let's go ahead and pick 52, right? Since we have 52 cards. Okay, so now we're starting to get into the bee's knees of all these things and whatnot. So if we have our gen and our gen takes that, we have something that's, reasonable here. But as we start changing these things around, you'll notice the randomness. Like say we were to take, let's limit this to 51. So we start to see some oscillation here with we have odd, 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 even, and this one doesn't really track with it. But if we start pulling enough of these, we're going to get into a state where every number that we limit in is either going to be even or it's going to start going odd, even, odd, even, odd, even, odd, even. And the reason why that happens is we have a silly little thing going on here to where the least significant bits with this algorithm, with doing this type of normalization, they tend to be less anthropic or less entropic. They tend to, what's the word? They tend to level out to a consistent pattern because they're not very noisy. They're not very random, those last 16 bits. So what we want to do really is get rid of that information, because if we start getting that information into our equations and things like that, that error is going to start multiplying on itself, or that, oh my gosh, what is the word when two things come together? I can't remember. I'll put it in the comments later. Evolve? No. Anyway. So what we really want to do is get rid of those last 16 bits. Otherwise, we're going to get a lot of our random numbers are going to start to stabilize over a period of time. So to do that, we want to keep this all in while we're doing the manipulation and bits like that on X. We want to keep it into the 32-bit integer kind of realm as we're doing our stuff with that. So what we want to do is we'll take our X and we want to zero fill in, do a bit shift where we move the last or the most significant 16 bits. We want to move them over 16 bits and push the stuff we don't want out. But we need to keep track of that sign, and we want to hold on to our sign there. We need it to stay positive for this. So we're going to zero fill. And that's the difference between the 3 and the other ones is, and the 2, is this one zero fills and keeps your sign all the way through. So it'll never create a sign. It'll never set that sign bit on the 32. But now we have a problem because you'll notice we'll start getting 0 because we're not limiting to the same factor. So we pulled this in, So what we need to do is take these 16 bits or get rid of these 16 bits or these 4 things right here so we can do the proper normalization. So we do that by going 1, 2, 1, 2, and that gets rid of 2 bytes, which is 16 bits. So now when we normalize, we get it back. And we have our random number generator that we own the seed of, right? So does that make sense? Like kind of what we're doing here? A no will still keep me going if nobody says anything. If you got any questions, go ahead and ask them. All right, 40 minutes into this and we only talked about linear congruential generators. But now, for those that have been waiting for the functional portion of this, this is not going to work for us because if you notice, using this generator function and doing all of this, we are trapped inside of, like, we don't own this seed. We have the initial seed, but we don't own the actual seed itself. It would be nice that every time we call a number, we say, give me a number, the next number in the sequence based on this seed. And then from there, it should just work. But it doesn't. It won't work for our needs doing it like this. We need to actually own that seed and we need it in there. If you notice, the only time that we get this seed, oh, you know what? This would have shown you. Oh, I had my seed wrong. Had I had that to 10, it would have shown you the, how would you say? Anyway, whenever you get the code to this, start playing around with it. Change what you initially seed it with. And from there, you'll be able to see that convergence on either the evens or the moving from odd, even, odd, even, odd, even I was talking about earlier. It's because I had the 5 there, and it doesn't work very well. It works much better with, how would you say, non-primes. But I had a prime number in there, so it wouldn't do it. Okay, so let's get on to the part where we start actually using ADTs. I just kind of wanted to go over that just a little bit. So number one, you could see the reason why not to use these for cryptography. They're fine for things that we're doing here with games and stuff like that. But when lives and identities depend on it, you really don't want to reach for math.random or, you know, any of the normal LCG generators. And this is why. There's issues with them as far as the randomness that they generate. So without further ado, let's move on to actually building this for our needs. Because we need to get this and have a way for us to keep track of our state, number one, and then pull random cards from, or pull a card from a random place in the deck whenever we go to select the card for the game. So to do that, we need to have complete control over that seed. So there's this really cool ADT that allows you to do this. It's a way to model state machines. You give it a certain state, it'll compute the next state, and then give you the result of the computation of that state shift. So that's kind of where the name state monad comes from. It just so happens, yeah, it keeps state and all that, but and its co is this thing called the store. I'm just throwing out words in there so you can Google them or do whatever if you're curious about the relationship between a state and a store. It's actually really cool, and it'll teach you a lot about the cat theory and things like that. So since we need to own the state, we're going to use this state monad to take care of that for us, right? So instead of doing it like this, and let's go ahead and we'll capture this formula. This is the part that we need. This way. Ooh, I changed my, hold on. I need to go back to layer 3. All right, so then here we just do that and that. So we'll keep that formula around, but pretty much all of this can go. We don't need any of this stuff hanging around anymore. So let's go ahead and grab Crocs, or using Crocs to get this going, we'll pull out a state. Oh man, I was hoping to get to the profunctor stuff today, but I don't know if we're going to have the time. So from here, we're going to pull this from crocs, and we're going to grab state. So this will get us the state monad that we're looking for. We don't need any of that. And when this comes back, so this state is defined as a object. Oh, sorry, it's my kitten. That has some sort of state and then a value to it. And it lets you build out a kind of a declarative flow of, based on a given state, how would you calculate some sort of value? And I guess it's better to kind of show an example of this, or like how it's used. So there's little helpers and things like that that we'll get on there that let you build these, but we'll go ahead and construct one real quick using kind of the longhand, so you can kind of see what it's like constructing one of these, right? So we'll go ahead and add our const rando again. And this rando is going to be different though, because it's not going to return a function, but it's going to wrap the function inside of a state monad. So with this, for now, we're going to have just a function that takes nothing and will get us back our state. So here, we'll just do this state, and this is a function. State takes a function that needs to go from whatever your state is and then return a pair of your state and the calculated value of that. So we're going to have to bring pair in, but we'll get to that in a minute. So since this is kind of imperative-y, like you can think of this as like the do notation in Haskell or things like that, what we're going to do is do our const seed is equal to, and then we'll just take this, y to here, and then we just paste this in, and that'll take what our seed value is, right? And now we need to have an actual value. So our value is just that calculation, value. And value is going to be our little bit shift and the things that we do here. Okay, so now we have this seed, now we have that. We have rando, we have s. So this, our seed itself, is going to come in on the state that we pass in. So that way we can have this state that gets passed into us. Now the state monad lets you both set and read from state. So we can read from it like we're doing here, but we can set it as well. And how we do that in this kind of way of using a state monad, return, is we're going to return a pair. So let's bring pair in. And a pair is just, we went over pair before. It's how we're holding our decks and doing our bits like that. No big whoop. So we're going to return a pair that is the value on the left side, value, and then our state is going to be on the right side. And what we need to do is assign this, and we used assign in the other one, and we're going to take that seed and we're going to assign that into S. So we need to bring assign in, or assign, and that is require crocs helpers assign. And this needs to be seed. Okay, and then we have our rando, then we have all of that, right? So now we have everything we need. Of course, it comes in undefined. We have everything we need to generate a number, right? So if we just call rando, we'll just call this S, and we'll call rando to get back our initial state or whatever. And if we log this, we see we get back our state wrapped in a function. So now we have this function that's ready for some state and ready to go, and we can compose them together, do things with all these state objects, and they won't run until we run them. So how we run them is we need to call this with our initial state, right? So all we do is, instead of doing this, we don't need that extra variable hanging out. We'll just do rando to get our state back. And here we'll do run with. And run with is how you run like the lazy things that are accepting parameters and stuff inside of Crocs. So we'll run this with a seed of 23. So as you see, we get back our pair with our seed or our value on the left. So it generated that value for us of a number from 0 to 1. And it went ahead and gave us back the, how would you say, the next state that we need to run it. So let's see, since this is a pair, we can just map over that right side. And actually, let's just grab the first so we can see what it did to the state. So remember, we came in with a seed of 23. So now if we look, oh, I'm sorry, second. We want the second of this. My bad. So if we look at the second, we notice that we got a new seed. So it went ahead and we put in 23 as the seed. It gave us back a new value, which is our value, and then our seed got updated. So another thing we could do, since we don't really care about what the previous value was, we can go ahead and use a chain on this. Because remember, with chain, rando, with chain, all it needs to do is return a new state. So we can chain this time and time again and get a new one back. So what it did last time is it fed the last seed into it, this seed here of 175 ... and then it fed that in the next time that we chained it. So every time that we chain, we get back a new seed. And not only that, but every time we chain, we get back a new random value. But it's the same value because we own the seed and we're starting with the state. So that's where the power of this comes in. And right now, this is just one thing on our state. We're going to throw our deck on our state. So that way, as each one of these operations happen, we can grab a new number, update the deck, update the seed, and have it ready for the next part in our game loop. And every time, all we're doing is updating the state. And that changes the state of the app. So this is a very, very powerful pattern and lets you do all kinds of wonderful things. But like I alluded to before, this is one way of doing this. Like you can manually construct these pairs. You can do things like that. You can do this if you want to, or if the code says, hey, this is what needs to be done, you can do that. Super easy. But the state actually allows, or the state monad has a couple helpers on the constructor, and that's get, modify, and put. So what we can do is get our get, modify, and put. I have a trailing space here, yeah, so I don't need any of that anymore. So let's get rid of pair, and then we'll get rid of this. Actually, we'll get rid of a lot of this. Okay, and we'll create a new one using the other attributes. Okay, so we'll do const, and we'll pull off, really, what do we need to pull off? We want modify. What's the best way to actually do that, though? The best way to do that, I think. All right, so let's do modify, and let's do get, okay? And we'll pull these off of state. So just to kind of see what they do, all right, so we'll pull that off of state. Let's get rid of this stuff for now, just so we can kind of see what's going on. We'll keep the run with, right? And we'll get rid of rando. Okay, we got rid of rando. We'll keep that. So let's go ahead and we'll call modify. Okay, and we'll call modify with nothing. And basically a modify with nothing, what it's going to do is it's going to take whatever state gets passed to it, and it's going to return a pair, or it's going to return another state that in its pair overwrites whatever the A is with, or we'll keep the state the way the state is on the first or on the left side of it, and then on the right side of it, what it's going to do is if we had a function here, it would run that state over the function and populate the right side of it. So we can see what's going on here. Working. Oh, I didn't update that. Oh, and you know what? Let's show get first, okay? So get's a little better. What version are we on of this? All right. So anyway, if we look at this, we now have our pair. And if we remember, pair is a bifunctor. So we can bimap over this, bimap over that. And, well, actually, let's not bimap. Let's just look at them, each one. So if I look at the first, I get back the seed of 23, which is what we passed in. And if I look at the second, I get back the seed of 23. So it's the same sort of thing, right? Well, and it's not modify, it was get is what I need to put in there. So if I do get, and I do it with, say, another function, like say I want to pull the seed off, right? And put it into a maybe. So what I could do is do a prompt with seed, and that's going to get me a maybe. Maybe. So, oh, this is the old version. Sorry, this is I forgot that I made these changes in a newer version. Oh no, it is this version. So wait a minute. Oh, yeah, sorry, it's going to be on the left side or on the first, which is a little weird. I think that might be a bug. I'll have to play with that. But what it does is it gets me the state, and oh no, that's right. On the right side, it keeps the state, and then we're functorial on the left side of a state monad. So it's basically like this. State, we can define a state as AS, right? So on the left side of the state is what we're mapping over, like anytime we call map or do things like that. And then on the right side of it is the actual state that's there. So sorry about that. So by looking at the first, what we did was it kept the state the same. It didn't touch that at all. See if we look here. But it ran over that function that we had here. Giving us our just 23. So instead of setting things up, like you can think of this as, because a lot of times with state, all we're doing is chaining things in, chaining things in, chaining things in. We don't really care a lot of times about whatever the value of the current state machine is or what the current calculated value is. Most of the time, we only care about the state. So this is a way to allow us to move the state and make it to where we can adjust it, do things to it because it's on the left side or on the part where we're functorial. That's not the state, it's the actual result. This will let us work on that state without adjusting the other state until we want to adjust it, right? So now when we want to set the state, that's where modify comes in. And that's where we'll actually do the modification on it. But right now, let's just go ahead and get this going using get, and we'll see kind of what get is, or how to use it, I should say, right? So the first thing we'll do is we'll create a function called pull random. All right, now the function that we're creating with pull random, what it does is it pulls, or it'll take some sort of integer, which is our seed, integer. That's going to be the actual seed that we have. And then it's going to give us back a state object that has the object there. So this will be our new state, which will be our, the thing we just had there with an object that has seed on it. And then from there, it's going to return, or the other side of the state is going to be a float. And these are actually backwards. It should be float object, but I don't know. I might change that. So basically on the, we'll leave it like this. So basically the result of this state machine, the result of it is going to be the float. And then the new state is going to be an object that has the state on it. So what we want to do is build a function that matches this. So we'll just do our const pull random. And pull random is the first thing we take is whatever our default or initial seed is. We're going to take that initial seed, and from there we're going to use that get function, right? So that function that we just looked at, get, which will get us a new state that just is populated with what the state is, because at this point, oh, you little kitten, you need to get down, okay? Sorry, hold on. Oh, you poor thing. So this state, we're going to basically get what the state is that gets passed in whenever we run this. And then from there, we want to go ahead and pull just the seed off of that, right? So we want kind of what we were doing before. No, kitten, you really need to go down. I'm so sorry. So sorry. So what we want to do is pluck that state off of there, because we really don't care about the rest of the state when we're pulling a random number. Most of the things that we want to do just works on that state itself. So since we already have this prop in here and all that, it returns a maybe, but we don't really want to work on a maybe. So we're going to option that maybe out. And we'll just do require crocs, and option is a point free function, point fee. That's how you say it with the speech impediment. And then we do option. And we'll make a just a quick little helper function here called pull seed, I guess. Pull seed's a good name. Good name as any. And what pull seed does is just going to take some sort of def. That's basically what we want to default it to. Actually, let's call this pluck seed. That sounds a little better. So we'll pluck the seed off. And this is going to take some sort of default value. And from there, we need to compose something in. So let's bring in a combinator. So we'll do const b, and this is the Bluebird combinator, or basically just, compose, I guess. And that's going to be crocs combinators, and this will be compose b. And that's the Bluebird combinator. So we'll come over here, and we're going to do a composition, which is option, and we're going to option it to whatever we say the default is. So if that way it comes back and seed's not available, we can just pass in to this function, if we don't have that seed, go ahead and use this seed. So that's why we're doing that option there, right? So then we'll do our prop, and we want to pull seed off of that. So now this is going to get us back a function. Once we pass that in, it'll get us back a function that's going to check to see if there's a seed object or property on an object. If there is, it's going to get us back adjust that value, and then once it hits option, it's going to just pull that out. Now if seed is not available, it's going to run it through that option on the nothing, and it's going to replace it with what the default is. So this will get us our I should have did this first. We do pluck seed, and pluck seed just takes an integer, and from that integer it gives us, or then it takes an object, sorry, and from there it gets us back another integer. And that's all this is. It's just a function that's curried, takes an integer, takes an object, and gives us back the integer that's on there. This really could be anything, but because we're not specifically checking for an integer. So one of the things we could do is do this prop and then do a safe to make sure it is an integer, right? So we could do a safe is number, and then it's going to check to see if it's actually a number, and if it is a number, then it's all good. Otherwise, it's not. Well, we'd actually chain in the is number. So this would be chain safe is number, df that, like that. But for these purposes, we don't really need to deal with it because we're going to own that seed. It's going to come from us. But if we wanted to make sure that it is a number, and actually we could use the is integer and cross. And is integer will tell you if it's an integer or not. But we're not going to do any of that. No reason to add any of that to this. For now. We might need it later if it starts giving us problems or whatever. Okay, so now we have our pluck seed. And what we want to do here is put in our pluck seed. Oops. We want to put in our pluck seed. And that will get us back our bits, right? That'll get us back our certain state, or the state that we have. So we can check this out by doing pull random. And if we do pull random, and we need to give it, of course, a default seed, that's going to be, I don't know, let's put in 45, right? Can I combinators? Okay, so now that gets us back our state that we're working on, and we will do run with, and we'll give it some state, run with, and we won't put in that seed, right? So let's do pluck seed, def seed. Sorry. Okay, so now we have our 45 that comes in on because we went ahead and pulled the seed out. So see how we have that? That's 45. That is our default going in, and then because we're doing that, it basically just, pulls that out, right? So that's why we have the 45 on the left. Now if we provided seed, so let's put in seed and we'll just make this leet. Okay, that's not leet. Oh my gosh, you are embarrassing yourself, sir. So you notice now that we actually have the seed, that comes in with the actual seed we provided. But if we didn't have the seed, df, if we didn't have it and we just pass in and run with normal object, that gets us our 45. Okay, so now we need to actually do the random, right? Like, we need to set this up to do the random for us. And we'll do that with modify, because once we provide the value, we need to actually modify the state in place. So instead of doing it the way we did before, where we... oh, did I actually pull out? I sure the heck did. That's really good. That's all right. We'll just write it out again. So let's make our rando function again. And rando is, of course, going to take an integer, and then it's going to take and give us back our state object float. Okay? All right, so now we do our rando. And because we are going to, when we did this, if you noticed over here on the right, this pair over here on the left part of the pair, the left part here, that's going to be what would get passed into a chain when we call chain. So that's basically going to be what our seed is for this. So what we want to do is take in whatever our seed's going to be, right? So we're going to make that x. And from there, We're going to do our little calculation here. So that's going to be const seed is equal to, I can't believe I deleted that stuff. How far back can we go? There we go. Okay, sorry about that. All right, so we'll paste this back in, and we basically just want these 2 lines, right? Okay, perfect. So now we have that. The only thing here is we don't really care about the state, right? We don't need to know that we're inside of a state, or we don't know that we're pulling something from state. We're just a function that takes something and then returns state back to it. We don't really need to, we don't want to pull anything off of it because this pull random takes care of that interaction for us, if that makes sense, right? So we're going to replace this with x. And that will get us back our anything that gets passed into us. In this case, it's going to be 45, as we see right here. And that will be what gets passed in here once we chain this function on. Now from there, we need to do 2 things. It's a 2-part operation. So number 1, we need to adjust our value. And at the same time, so we can return the actual value of our bits back. And at the same time, we want to modify what the current state is to represent our new seed. So it's a 2-part operation. Not only is it calculated twice here, but we need to do 2 things for our state. We want to update the state and return a value. So that's where modify comes in, right? So with modify, we can go ahead and modify the actual value. And we'll do this. And let's go ahead and pass in seed. So now what happens here is we're going to go ahead and once we get done with all of our bits, we're going to calculate our seed, do all that. We're going to call modify. And what modify is going to do is take our function and then apply the state to it and then set the state to the result of that function. So we're going to take this seed value and just assign it to whatever the seed value was before. That's it. Nothing to it. And then the other thing we want to do with this, of course, is we need to provide the random number that we calculated, right? Like we need to get our value from 0 to 1 because just the seed itself isn't helpful. We need to actually have the value for it. So what we'll do is then map over it because remember, this is a state, so we're going to return a state that's been modified and also has been mapped over with the constant of whatever that value is. Because remember, map takes a function. So we're going to bring in another combinator here. This is the k combinator or the constant combinator. If you're using Ramda, it's the same thing as always or things like that. So we'll go ahead and bring in constant, and this is basically just a constant function. Anytime it's basically pointed, so anytime that you call this function, it's always going to give you back the same value. So then we just pass in value, and that's going to be what it provides. So now let's just make sure we're not broken anywhere, and it doesn't appear to be. So what we need to do now is we have this seed, so we need to apply this random number generation to it. And we do that with chain. And basically, you'll notice chain, all of these monads and things like that, they're very effectual. Like they have an effect or the thing that there's this guy I watch on YouTube, Bartos, and I never say his last name properly. But he has this wonderful thing. He says these ADTs just add some sort of embellishment to the value, right? So in this case, the embellishment that we're adding is we're updating and reading from state, or we're updating a state. That is the embellishment that we're having, and then providing the result of that. So when we chain, anytime you'll notice, so if I chain like a maybe to a maybe, that will change what the maybe is. If I chain a reader, it's going to read in what the environment is. It's how you get these embellishments to trigger is through this chain function. or to see the effect of them, right? So now we have this function that's set up in our typical Kleisli way. We take sum A and return an m of A or an m of B. So we just chain in this rando function now. A rando. And you'll notice now we get back our random value. And if we were to actually look at what the second is here, we see that it updates our state. We started with the state of 45. We didn't pass anything in there, right? We didn't pass in state or a seed, so it's using this seed. But, I mean, if we pass in a seed of leet, notice we won't get back leet, right? We're going to get back what the new state was, or what the new seed that was generated was. And then that'll come back for you. So that's, you know, this is kind of how you do silly little things like this, right? So the other thing we need to do now is these values that we're getting on our first, they're not really what we want for this implementation. We don't really want a value from 0 to 1. What we want is a value that we can limit it to based on the size of our deck, right? So we need something that we can change the value to based on something. So we had that old limit function. Remember that a little bit ago? We had our little limit function. So we're going to change this one to be limit index. And it doesn't need to be that specific because it's basically just a limiting function that will get you something from 0 to whatever the top of that is, -1. But what else? We're still going to call it index. So all we do is it's a curried function. Let's write out our type here. So we will do limit index, takes a integer, and from there it's going to take some sort of float value, and from there it's going to get us back an integer that is no greater than this -1, whatever our initial integer is. So we do that with our silly little floor stuff. So we'll just do our math.floor. And actually another thing we could do instead of flooring is we could just OR it to a 0 and get rid of that. So since we're doing the bitwise stuff here and doing all that, if we do a bitwise OR to 0, it will still clip off the remainder and it'll keep it in the positive for us. So, but it has the benefit of doing it with a signed 32-bit integer. So since we're doing all this, how would you say, bitwise operations and stuff, instead of using math.floor, if you need something like math.floor and you want to be all cool or whatever, you can do it just by bitwise ORing in a 0. And that'll do the same thing. I'll let you play with the bits and you can pull out your little programming calculator and see why that is. And just always remember when you do a bitwise operation on a number inside of JavaScript, it's always going to work on it as if it's a 32-bit signed integer. Always just keep that in mind, which is what we need for this. So all we're going to do is take our x times length, okay? And we should be good from there. So let's get this kind of set up. It's nice that we're doing this pull random, do this, do that. But we really want to set it up in a way that we would be using in production. Like when we go to integrate this in our game, we're not going to be using it like this. So let's just do a little contrived way to set this up, right? So we'll just do a state.of and we'll point to, we'll just point to null, right? So we'll just point to another singleton there and we'll point to null. So this is basically going to set it up to where there is a null on the right-hand side or on the functorial side, the part where our result is. And then here we're going to do a .chain and we'll pull in the pull random. And let's just do a seed here. Const seed is equal to, let's make it 76, like the gas station, right? Okay, so from there, we're going to pull in our random. We're going to pass that seed in. And, well, let's just see what that gets us real quick. Just make sure that, oops, let's just make sure all of this is working as we expect. So we want to do a run with here, and we will just run it with, I don't know, we'll just throw something in here. We'll do deck.false, right? Because eventually state.chain function required, pull random takes that. What's going on here? Okay, hold on. So that's coming here, that's on 108 of that, which comes in on, where is that, 41. So it is this one, and we need that to be pull random. So we have our pull random, which takes our get, what's going on here? So that will take our def seed. Hold on, real quick. I got something silly going on here. So if we run with that, this is not actually a function. That is that. So that is not going to work. That's not going to work, eh? So if we take this and take that, I don't like that. I don't like how that is set up. So this would be our state of that. Then that's going to get off of that. Let's just see something real quick. Okay. All right, we'll fiddle with that here in a little bit. But just so you can kind of see what's going on with all of this, all we really did was we start off with our chain, right? And then we have our pull random where we can put in a seed. So we could either do it like that, or we could do it like this, right? So we can put our seed in there, which is 76. We'll just throw in pull random. And that state.of is going to populate the part where we're functorial, or the part that we're expecting to get the seed in and all that. It's going to pass it to there. So by doing this state.of, it's basically going to pass that to here. And this is probably what we want. Okay, so then we just do this and that, give it a save. And if you notice, unlike our last results on the previous episode, we get back a different, or the same value every time, right? So the other thing we can do is every time we chain this, we get back a different value. And that will pull a new random value. But we get back the same one every time. And to make this a little easier to read, we can take the same thing and then just map over it. And then from there, we'll just do our limit index. And we'll limit this to 52, so we'll pretend this is the first draw in our 52 deck. And we get back a 2, but we get back a 2 every time. So this is going to grab the third element in that deck because we're normalized from 0 to 51, right? So this is going to get back our third element in the deck, and it would randomly pick it. So then if we do this again, it would get back 11. And if we do it again, the next number we get is 35. So it seems very random, right? But if we go ahead and GC this, or comment that out, notice we get 2 again. So this is exactly the solution that we were looking for to take care of this, right? Now, I went a little long on my explanation of the LCG. A lot longer than I anticipated. So I wanted to get through a little bit more than just this stuff today. I wanted to also kind of show you how we have, since we have 2 things going on here, we can actually use a strong profunctor, or we can use an arrow with that wraps a pair inside of here. but I'm not going to be able to get to that today because we're already coming up on an hour and a half. And I don't want to make these too long. So I might have to punt on that and do that next week. I didn't mean to take so long with the other stuff. But that means, well, let's just recap what we did, okay? So we went through and we explored this algorithm, this linear congruential generator. We talked about some of the strengths and weaknesses of it, mostly the weaknesses, but we talked a little bit about the strengths and what it does for us. And we played around with different values here, and then we implemented one because we're using the same type of data type, a 32-bit signed integer that the GCC uses. We went ahead and matched with this one, right? Then after that, we put that into a function generator, and we generated all the stuff, got all that going, and found out that that imperative solution wasn't going to work for us. So what we did is we then talked a little bit about the state monad and put all that together, right? So next time, what we're going to do is explore a couple profunctor called arrow, and we're going to see how we can kind of split this two-part interaction into two separate flows to be worked on again. So yeah, I kind of made a mistake and went a little mathy on this one with the LCG, and I apologize for that. Hopefully you find it beneficial. But we'll get more next time into the functional part of that. I don't know why I went on. I know why I went on. I like doing things like that. But I didn't mean to take away from the actual focus of this lesson. So I guess next week at 3:30 on Saturday, we'll finish this up and we will get this going into a, how would you say? We'll get this going into a flow that works with the deck, and we'll start randomly selecting cards from our deck. And to do that, we're going to have to move our deck code and all of our card code to be able to work with state. So we'll do a little refactor on there to kind of get it ready for state and see how much of it we don't need to change, because the point of doing things like this is you don't need to change things, right? Or you shouldn't have to change things too much. These things should just wrap, all these ADTs should just wrap around your existing functions. But I guess that's all I got for today. Thanks for coming by. Sorry about the kind of propeller hat episode. Next time for sure I'll focus a lot more on the ADTs and less on the math. So I hope you guys have wonderful weeks, and I look forward to seeing you later. Bye.